Okay, good morning, everybody. Welcome back after a week since we've last talked about evolutionary robotics. We got a number of housekeeping items to get through first before we dive back to or pick up our history of evolutionary robotics. So, just as a reminder, last Tuesday we talked about the first two evolutionary robotics experiments, and right at the end of lecture 7, we saw an example of a neural network that can distinguish between triangles and rectangles, but has no recognized triangle and recognized rectangle module in it. The robot equipped with that neural network was able to distinguish between triangles and rectangles by combining a particular way of moving in its world, so exploiting its body, and having a particular neural network that was able to pull together information about movement, time, and space. You might remember there were two fovea, two different parts of its visual field that it focused on, and the neural network was able to detect the time delay between one of those fovea going dark and the other fovea going dark. As I mentioned a week ago, that is probably the best example we'll see in this course of what embodied cognition is all about, and in a way what evolutionary robotics is all about, trying to evolve bodies and brains of robots simultaneously to exploit the body and motion and time to solve problems in the real world and exhibit intelligent behavior. Okay, obviously no class last Thursday. That was last Thursday. This past Tuesday was town meeting day, no class. We're going to start in today on a sub-theme in the history of evolutionary robotics called minimal cognition. I'll pause here for a moment and we'll come back and talk about minimal cognition in a moment. Let's skip over and talk about the assignments. You're working on assignment 5 now, which is due this coming Monday. Assignment 5 is one of the longer assignments. We're sort of taking a break midway through here in the 5th assignment to do a little bit of housekeeping. You're going through and reorganizing all of your code into an object-oriented hierarchy. So as I mentioned last time, if you're not familiar with object-oriented programming, now is the time to do so. And as always, make sure to brush up on your OOP skills and tackle assignment 5 long before Monday at 11:59 p.m. I also just put up the link for assignment 6, which won't officially be assigned to you until this coming Tuesday. But for those of you that want to work a little bit ahead, I thought I'd just put it up there. Any questions about the assignments? Everything going okay? All good?
Would we be able to talk about the first question on the last quiz again?
The first question on the last quiz. Yes, Missy, can you remind me what that question was?
Yeah, it was about whether or not the spikes in recognizing a triangle are longer or shorter.
Yes. Okay. So that question was about exactly what I just mentioned, the gantry robot that's able to distinguish between triangles and rectangles. And the question was asking about which time interval indicated a triangle or a rectangle. Was it a longer delay between the darkening of the first and the second fovea that indicated a triangle, or the other way around? Is that what you're asking about, Missy?
Yeah.
Okay. So I'm sorry. So what is your question about that?
I guess I would have thought that a longer interval would have made more sense because there's more space that changes.
I gotcha. Okay. So right. So whether it's longer or shorter depends on whether the triangle is right side up or upside down. And the way it's drawn in the slides, it was meant to demonstrate with one fovea here and one fovea here that the triangle was right side up. But if that was not clear from the slides, I think that's fine. If someone can just drop a note for me in Teams so I remember, I can go back and check that if you put in that it was about delay, but you put in the wrong delay for that question, I'd be happy to give you back the half point for that question. Sound fair?
Sure.
Okay. All right. Thanks for bringing that up, Missy. Okay. Any other questions, assignments, quizzes, anything else so far? Okay. All right. So more housekeeping. We are going to, in the very last lecture of this course, talk about Xenobots, which I mentioned briefly at the beginning of the course. This is some very recent work between my lab and a biology lab at Tufts, creating evolving robots in simulation. And then instead of building them out of metals and electronics, we build them out of frog cells, specifically out of the cells taken from Xenopus laevis, thus the name Xenobots. The Xenobots are currently in contention in Stat Madness. I don't know about you. I'm not much of a basketball fan, but I know this is March Madness. So there is a particular bracket going on at the moment between new technologies that have emerged in the last year that might be useful in the not too distant future for biomedicine. One of the potential applications for Xenobots, again, not anytime soon, is that it might be used for internal medicine and non-invasive surgery. In a very future version of Xenobots, you might be actually able to swallow one as a pill, and that pill is actually a robot. It can find problems in the body and fix them. Again, a long way off, but hopefully someday it'll be useful for biomedicine. So I'm hoping that some of you might be able to help us with our bracket. So I'm going to drop the link to Stat Madness here in the Teams chat. And if you're willing, follow that link and it'll bring you to the bracket here. If you scroll down about halfway on this page, you'll find Tufts University. So this is work we did in collaboration with our biologists at Tufts. If you click on Tufts, it'll give you a description of our Xenobots on the left here. We're currently competing against MIT, a project from MIT, which is also extremely interesting and could be very useful in the not too distant future. So please have a quick scan of these two technologies and cast your vote for one or the other. Obviously, we're hopelessly biased, and we'll hope that you'll vote for the Xenobots. We're a little bit down in the bracket at the moment, so we could use a little bit of help. Okay, that's Xenobots and Stats Madness. Thank you very much for that. Okay, back to CS 206. So today we're going to start in on our discussion of minimal cognition. This is there are a series of papers that were published in the late 90s, so the very first years of evolutionary robotics, which after the fact became known as minimal cognition. These papers taken together were an attempt to get at intelligence by evolving the simplest possible robots we could. They had the simplest bodies, the simplest environments, the simplest neural networks you could imagine. But once they are evolved, if you look at them, you might say that they are exhibiting many of the building blocks of intelligence. So it's another way of coming at the question of what intelligence is, which is what is the simplest possible creature, and possibly what is the simplest artificial creature that is capable of planning affordances, distinguishing between self and non-self, perception, making categories, forming categories. We're going to talk about all of these building blocks of intelligence in a moment through the lens of minimal cognition. Okay. All of these minimally cognitive creatures are equipped with a particular type of neural network, CTRNNs. These are not so popular in the machine learning community, but they are very much useful in robotics. So we're going to spend all of today talking about CTRNNs, what these particular neural networks are. And then if we have time, we might move on to lecture 9, but we probably won't get there until next week. And we'll look at the evolution of some of these minimally cognitive agents using CTRNNs and what features of intelligence, what building blocks of intelligence are they capable of evolving the ability to exhibit. Okay. That's today. Next Tuesday, I'm going to be reviewing proposals for the National Science Foundation. So I will be officially a member of the U.S. government on Tuesday and not available to teach. So one of my PhD students will be here giving a guest lecture. He or she, I'm not sure who will be visiting you yet, will be talking about their research. So you'll be able to see some of these concepts we've talked about so far being developed in the moment in a particular project. I've asked my PhD students, whoever does come and speak to you, to spend half the time talking about their research project, and then to spend the other half of the time in discussion with you about sort of life as a PhD student. So how did they decide to do a PhD? How did they decide on schools? How did they apply? What's life as a PhD student like now? How does it differ from what they imagined? So for those of you that are considering going on to graduate school, please prepare your questions and be ready to ask them on Tuesday. It's been a long time since I was a PhD student. Things have changed greatly since that time. So this would be a great opportunity for you to get some of your questions answered about whether grad school and grad life is right for you. Okay, all right, so Lecture 8, Continuous Time Recurrent Neural Networks. We are going to start with brushing up a little bit of our calculus. You'll notice that one of the phrases in the name of this neural network is continuous time. Pretty much everything, most of the things we do in computer science are broken down in discrete time. You're already working with a physics engine where, at least from your perspective, there are discrete jumps in time. But of course, the real world doesn't work like that. Time is a continuous property. And hundreds of years ago, that became something that became an increasing interest to mathematicians because it was hard to describe a relationship between variables, two variables x and y. If we assume x, or the horizontal axis here, is time, and y is some variable we're interested in, like amount of algae in Lake Champlain, most properties in the real world change continuously over time. So we can think about, for example, the slope, or the rate at which something is increasing or decreasing. And as you remember from high school, slope can be written as the change of height divided by the change in time, or change in the horizontal axis. But what happens when we want to try and describe mathematically change at an infinitesimally small delta x, or if the horizontal axis here is time, delta t? It becomes very difficult to do. One way of looking at this is to look at a difference equation. Difference equation says we want to try and understand the value of some variable at some point in the future, t plus 1. And we wanted to describe it as its current value plus some time that elapses. So if the difference in time between t and t plus 1 is 1 day, whatever this variable is increasing by 1 each day, right? Perhaps we're more interested in shorter periods of change in this variable. So maybe we want to try and write this down as the change in the value of this variable over half a day, if it's still the same relationship, plus 0.5. But if we want to describe the rate of change in this variable, again, for an infinitesimal difference in time, difference equations don't work anymore. A lot of the mathematics pre-calculus didn't help us be able to describe how things change continuously over time. So one of the greatest inventions of all time was the differential equation. Again, hopefully you remember this from high school, or at least first year calculus. We have some variable x that is changing over time t. So the change in x as a function of change in time, but we are no longer specifying how much change in time that is. So we can write this as dx over dt, or just to keep things simpler, we can write x prime, and the prime here is going to remind us that whatever is on the right-hand side of this differential equation is describing how this thing changes over time. Okay, so we're going to use differential equations to describe CTRNNs because we're going to be interested in how these neural networks change continuously over time, not discretely from one point in time to the next. Okay, so let's try and bring together differential equations and neural networks. Let's jump back to difference equations for a moment, which describe discrete changes in a variable as a function of discrete jumps in time. So again, going to introduce a little bit of nomenclature here. We have x1. So imagine we have a bunch of x's. We're talking about the first one. We want to know how this first x of many x's changes from t to t plus 1 and then t plus 2 and t plus 3. Some of these, some such difference equations, they may be a function of their own current value and some other stuff. So if we bring back our basic equation that describes a neural network, if we think of x1 as the first neuron in a set of neurons in a neural network, we can describe the new value of x1, the new value of this neuron, as a function of sigma. Remember, sigma is an activation function that squashes whatever value is inside to a value within some preset range. What are we squashing? Well, we are multiplying the value of all of the incoming neurons to x1 by the weight of the synapse that connects neuron 1 to itself, plus the weight of the synapse that connects neuron 2 to neuron 1, and so on. So you can actually, if you have a set of n neurons in a neural network, you can actually write them out as a set of difference equations. x1 t plus 1 equals this thing. Next difference equation, x2 t plus 1 equals the same thing but with different w's. So we have a second difference equation for the second neuron, and so on. Okay. But again, that's going to describe a neural network in which values in that network increase or change discretely from one time interval to the next. If we want to create a neural network in which all of the neurons' values are changing continuously over time, instead of a set of n difference equations, we can write out a set of n differential equations. If we have a neural network with 10 neurons in it, we have 10 differential equations. And I'm going to just change my notation a little bit here. So we're going to switch from x to y. So y is going to be the value of, y sub I is going to be the value of the ith neuron in the neural network. And y prime sub I is going to represent the rate or the way in which the value of neuron I is changing over time. Okay, so again, I'm just drawing one here, and I'm going to use the subscript I to remind us that this is the ith neuron among many neurons. You'll notice I have my red box here, which is meant to be a reminder to you to annotate the slides. What we're going to do over the next few slides is build up this differential equation that describes how the ith neuron in the CTRNN changes. So the spacing here, you'll notice the spacing. Try and follow the spacing as you're annotating or writing this down and following along, because we're going to be adding material to this equation as we go. Okay. Again, there's a fair bit of math in this lecture, so I definitely recommend, if you haven't already, get out a piece of paper and write down and follow along as we go. It'll be much easier for you to absorb this material. Okay, so we're describing how the ith neuron in the CTRNN changes over time. The first term that we're going to put on the right-hand side is minus y sub I. So what this is telling us intuitively is that the way in which y sub I changes, the rate at which y sub I changes, is the negative of its current value. Okay, I'm going to draw a little bit. Here to sort of help you build up an intuition for how this all works. Okay, I'm not sure how this looks within Teams. Can everybody see the T and the Y here? Just type a yes or no into chat. All good? Okay. All right. So we're going to assume we have 0 here, and we can have negative values of y. We can have positive values of y. When we're dealing with differential equations, we're describing how they change over time. So we need to introduce an additional concept, which hopefully some of you remember from calculus, which is initial conditions. We need to set some initial value for y sub I, and then we can use the differential equation to compute how that initial condition or that initial value changes over time. So let's assume that we start with an initial value of +1. That's going to be the initial value of our neuron. We plug that value into the right-hand side of our differential equation, which gives us back what information? What do we know now that we've taken this initial condition and plugged it into our differential equation? What do we know about y sub I? So if we plug in +1 here for y sub I, the value at t0, we have y prime sub I equals -1. What does that mean? Any ideas? So the rate of change, Henry says it will switch between positive and negative. So Henry's got the right idea, but we're jumping ahead a little bit. We're just trying to think about the rate of change at the current moment, at t of 0. As Lucas says, we know the slope at that time. The slope, right, y sub I, the slope, the rate of change is negative. So that means however forward in time we go, at that moment, the value of y sub I is decreasing. This equation says nothing about the amount of time we should jump forward. So we're going to just jump forward an arbitrarily small amount. I'm not going to write any numbers on the horizontal axis here. But if we move forward in time a little bit, this differential equation tells us that the value of y sub I decreases. So at some short period of time in the future, the new value of y sub I is 0.8. If we pause for a moment at this point in time, when the value of the neuron is 0.8, what can you tell me now about how the value of this neuron is likely to change if we continue moving forward in time? We take this value, 0.8, and we plug it back into our differential equation. We plug it in the right-hand side, which references y sub I. The value of y sub I is now 0.8. We plug it in, so we get the rate of change, or the slope. The current slope now is minus 0.8. So as Lucas says, it's still decreasing. Andrew says it's continuing to decrease. Has anything changed? The value of 0.8 the value of y sub I has changed. It's changed from 1 to minus 0.8. So what does that tell us about the rate? The rate has changed. As Lucas says, the value of y sub I is now decreasing at a slower rate. So if we dropped from +1 to 0.8 before, maybe now if we move forward again, we only drop to 0.7. What happens at the next, if I go forward in time and pause again and ask the differential equation for the value of y sub I now, and jump forward again and again and again and again. What can you tell me now about this line, which is describing the value of y sub I continuously over time? It's not a series of line segments like I've drawn here. It's a curve. As Lucas mentions, it's going to go closer and closer to 0. It's going to approach an asymptote, but never reach it, which is 0, right? So as we continue, the further out we go, the differential equation will say minus 0.8, minus 0.7, minus 0.75, minus 0.72, minus 0.721, and out at infinity will eventually reach 0. Okay. Let's reset our neural network. Assume that the neuron has exactly the same differential equation associated with it. But now I'm going to set a different initial value or a different initial condition, which is we're going to set the value of the neuron y at t0 to -1. How does the value of this neuron change continuously over time as we move forward in time? It starts with the value of -1. What does y sub I do over time now? The way we know is we take this value, we plug it into the right-hand side. We plug it into the right-hand side of the differential equation. And then as Lucas mentions, we're going to approach 0 again, but from the bottom. So when we plug in our value to the differential equation, we get y prime sub I equals +1, -1, and we put the minus in front. So the rate of change at this point in time is +1. We're going to start to race upwards towards 0. But as we do, we're going to reach -0.8. If we plug that back into the differential equation, it tells us that the rate of change at this moment in time is now +0.8. So the rate of increase is also decreasing and will approach the asymptote of 0 again. Okay, so you can continue playing this game, and you probably see now that if you pick any initial value for y sub I anywhere between -1 and +1, it will always approach 0 and approach it at a slower rate. C-tRNNs, as you'll see in the reading for today, were inspired by neurobiology, by the way that neurons actually behave. Why did the creators of the C-tRNNs write down this differential equation? Why did they include this term? It's meant to represent something about the behavior of neurons. What is it? Any biology students here? Any neurobiology students? If this is describing how a neuron in your brain behaves, it's very active, either very positively active or negatively active, but gradually it will always return to the same value, 0. What is this meant to be representing? Anybody know? The action potential, as Toby mentions. So neurons, typically in animal brains, they're lazy. If they're not being stimulated by neighboring neurons, they will return to their action potential, or their in this case, their resting potential. So what is their default rate of doing something if they're not stimulated? Usually it's not much. So if we did not have this -y sub I, if we wrote a differential equation that said y sub I, y prime sub I equals 0, that means the rate of change of the neuron never changes. If we set it to -1, it would stay at -0.1. If we set it to 1, or we stimulated it to +1, it would remain at +1. That is not how neurons behave. If they are not externally stimulated, they will relax or rest back to a default level. Okay. All right, so we're going to keep developing this equation as we go. And as we do, we're going to add in some math where each term or each variable that we add is meant to represent or make y act more like a real neuron. Okay. Let's introduce tau now. I apologize for the fonts in my slide here. This should be curvy T. Tau. Tau is meant to represent it indicates whether this neuron is a slow to react neuron or a fast to react neuron. Okay. You'll notice that we've written the tau on the left-hand side, which you may or may not have seen in your calculus classes before. One thing you can do is you can divide both sides by tau sub I, which will give you y sub I, y prime sub I equals minus y sub I divided by tau sub I. The reason we've written it on the left-hand side is because now we're being lazy. We don't want to write a long equation as a ratio or a fraction. Okay, so we're going to be thinking about tau sub I as a denominator on the right-hand side. So try and keep that in your head as we go. Okay, you'll notice again in our notation that we have a sub I associated with tau. So this is a value that is associated with the ith neuron. Remember that if we have a 10 neuron CTRNN, we have 10 different differential equations. They all have minus y sub I in them, meaning all of them will relax back to zero if not externally stimulated. But each of them has their own tau sub I. So if you think about the value of tau sub I being different for different neurons among the set of 10, now it means that these neurons are going to start to behave differently. When we first talked about neural networks, we associated weights or values that dictate how one neuron influences the other. These are parameters that we can alter to alter the behavior of the neural network. Same thing goes for tau. If we have 10 neurons, we have 10 knobs we can turn. We have 10 taus, and by turning those knobs, we alter the behavior of the neurons in this neural network. What happens if we have a tau? Well, and for our purposes, we're going to keep things simple. We'll assume that the tau sub i's are always positive values. They don't have to be, but for today, let's just assume they're always positive. What does a low time constant do? Meaning tau sub I is very low. It's very close to its minimal value of 0. Tell me about how y sub I starts to behave. Actually, let's go back to another example. Let's start by setting the initial conditions, the initial value of y sub I to +1, and assume that this particular neuron has a tau sub I that is very, very, very close to 0. What does the curve look like as we move forward in time from y sub I, if its initial value is 1, and we have on the denominator tau sub I, where tau sub I is very close to 0. If tau sub I is very close to 0, as Lucas mentions, we now have, it's going to decrease very fast. We have a denominator that's very, very close to 0, meaning the right-hand term is going to be very, very, very is going to be very, very fast. It's going to be a very large value, and it's still negative. It's a very high magnitude negative number, minus a million, minus a trillion. That means the value is going to rocket down towards 0 very, very quickly. So if you have a tau sub I, you can think of this as the Woody Allen neuron, or the character Woody Allen in most of his movies. He's very neurotic, which is kind of an interesting pun here. And very sensitive. Any slight stimulation, and Woody Allen goes crazy in his movies. He's all over the place. He's ecstatic, he's depressed, he's ecstatic, he's depressed. Very, very sensitive. It's very easy to push Woody Allen into very large oscillations with just a very slight nudge. Okay, so I mentioned oscillations. We can imagine if tau sub I is very, very large, that if we move forward in time even a small distance, that the rate of change is so great that it's now a negative value. We still have the same neuron. We still have a tau value that's very close to 0. If we move forward in time from here, what's the new value of y sub I? We're still assuming it has a tau sub I that's very close to 0. What's the new value of y sub I as we move forward from here? We've gone from +1 to minus 0.99. What happens next? If it's not clear, you can take minus 0.99, plug it back into this differential equation. We have minus 0.99 on the right-hand side divided by tau sub I, minus 0.99 divided by 0.00001, something very close to 0, which gives us minus 0.999 divided by 0.00000, which is now a very, very large positive number. Should I write this out? Is that helpful? So minus sub I equals minus 0.99999 divided by tau sub I, which is a very, very large number. So you can see now that, I'm sorry, that should be y sub I prime on the left-hand side. So now we have the rate of change, y prime is a very large positive number, and we go rocketing back up, but rocketing back up by slightly less than we did before. Tell me about the curve for this y sub I as we approach t equals infinity. What does this curve look like? Have I lost everyone, or is it somewhat obvious? It's a wave function or an oscillation, right? We've rocketed back down, which gives us minus minus, so we're going all back up again. We get back here to plus 0.98. If you plug plus 0.98 into the equation on the slide, we're going to rocket back down again. And eventually, this Woody Allen neuron will approach 0 as before. So as Logan mentions, we have damped oscillations. If we have a very low tau value, it's not damped very much. 1 minus 0.99 plus 0.98 minus 0.97 and so on. Okay. Let's go back to, let's reset our value to plus 0.1. Let's change tau sub I now to a very, very large number. Let's assume it's positive 1 million. So we have a very high tau value. We've altered the parameter describing y sub I. We've switched tau from a very low number to a very high number. What does the curve look like? How does y sub I change over time now if we have an initial condition of plus 0.1 and we have a tau sub I of plus 1 million? What does that curve look like? Again, if you're not sure, you can plug in these values. We have an initial value of y sub I of plus 1. So you can plug that into the right-hand side. So we have minus 1 on the right-hand side. We divide both sides by tau sub I. Tau sub I is 1 million. So on the right-hand side, we have minus 1 divided by 1 million. How does y sub I change over time? Parker and Logan are answering me here. It will converge very, very slowly to 0, right? So the rate of change is a value that's very close to 0. So the new value at some point in the future is also very different. And this value, this neuron is also approaching 0, but at a very, very, very slow rate. This is the Eeyore neuron. Eeyore was the character from Winnie the Pooh, who was pretty relaxed. It was very hard to get Eeyore to do anything. With enough shoving, Winnie the Pooh could eventually get Eeyore moving, but very, very slowly. So by tuning the value of tau, we can tune how sensitive the neuron is to initial conditions or values that are impinging on that neuron. For now, it's us, something from outside the neural network that's setting the value of the neuron and then seeing as time unfolds how that neuron responds. So far, so good. So again, you can imagine 10 different neurons. Each of them have their own different tau values. So some of them are going to be Woody Allen neurons, very sensitive and also oscillating crazily through time. Others might be Eeyore neurons that are changing their values very, very slightly. But all of them have minus y sub I. They are all quickly or slowly or in different ways approaching zero. Okay. Let's add in a little bit more detail to our differential equation. This hopefully looks a little familiar to you. So at the moment, we're assuming that all of the neurons are disconnected. We have 10 neurons and they're only being influenced from some value from outside. But of course, that's not true in both artificial and biological neural networks. They are influencing one another. And we do that by connecting neurons together with synapses. And for each synapse or edge connecting a pair of neurons, that synapse has a W associated with it. We have a whole bunch of W's associated with the ith neuron. We have J of these W's. We have N of these W's, which are the N incoming neurons. So if this is neuron I here, we have 1, 2, N neurons. And for each of these N neurons, there is a synapse connecting that neuron to the ith neuron. So we're assuming in CTRNNs that they are fully connected, which is a little bit different from what we've seen before. In most of the neural networks we've seen before, there's a layer of sensor neurons. And then below them is a layer of hidden neurons, and sensor neurons only connect to hidden neurons, and hidden neurons do not connect back to sensor neurons. It's partly connected. Here we're assuming that if we have n equals 10, in our running example here we have 10 neurons. We're assuming that for every neuron there are 10 incoming synapses. And because it's 10, it means there is also a WII. There is also a weight, a synapse that connects neuron I to itself. Okay. So we've put this summation on the right-hand side of our differential equation, which again is something you've seen before. So in order to compute the rate of change of y sub I, we're computing y prime, we're going to compute the total influence of all of the other neurons on the ith neuron. And that influence, that weighted sum, which we've seen before, the weighted sum is not going to set the new value of y sub I. It's influencing the rate of change of y sub I. Let's imagine we compute this total raw sum. We don't know at the moment what the values of yj, the other neurons, are. And we don't know what these 10 W's are. But let's assume that when we take this weighted sum, this total sum is a positive value. Doesn't matter at the moment what it is. What does that do? What does that tell us about the rate of change of y sub I? How is it if all of the presynaptic neurons, all the neurons that are connected to and influencing the ith neuron, if their total influence taken together is positive, what does that tell you about the rate of change of y sub I? What are those other neurons, quote unquote, trying to do to the ith neuron? There are other influences. Logan says inhibiting. Not quite. Remember this neuron, before we added this raw sum, no matter what tau was or what y sub I was, it was always trying to approach zero. If the total sum is positive, whatever the rate of change of y sub I is according to the current value of y sub I and its tau sub I, it's adding some positive number on the right-hand side of this differential equation. What is increasing the value doing? It's a positive number. How does that influence the curve of any of the ith neuron as we move forward in time? Alex says the rate of change approaches the sum of the neuron weights. That's true. If the weighted sum stays constant over time, then that means the neuron will try and approach that weighted sum. That's true. The weighted sum at the moment we're assuming is positive, so it's increasing the rate of change. So if y sub I and tau are causing the neuron to decrease, and this weighted sum is positive, the positive is trying to either decrease the rate of decreasing or increase the rate, right? It's trying to pull the neuron up. Logan mentioned it's inhibiting. It's actually exciting. It's trying to create a more positive value of y sub I. If this sum is positive, it is increasing the rate of change of y sub I. If the weighted sum as a whole is negative, then it's inhibiting the neuron. It's causing the rate of change to decrease. Okay, everyone see that? If this raw sum is 0, then it means that this whole term disappears, and this raw sum, if it's 0, has no influence on the rate of change of y sub I. Okay. As always in calculus, this gets a little tricky because we're not thinking about the value of y sub I, we're thinking about changes to the rate of y sub I, how it's being influenced. And there are now 3 different influences on how y sub I changes as we move forward in time. There is the current value of y sub I, there is tau sub I, and there is this weighted sum. Perhaps y sub I is... this term here maybe is negative, meaning that it's trying to cause the rate of change to decrease. This other term may be trying to cause the rate of change to become more negative, if this is a negative value. If this raw sum is positive, it means it's trying to make the rate of change increase. So there's these different influences. Okay. We talked about the biological equivalent of this term, which is resting potential or action potential, that neuron wants to sort of just relax back to some value if it's not being stimulated. The tau term also has a biological equivalent. There are certain neurons in the nervous system that are more reactive to whatever is happening to them. And there are others that it takes much more influence from outside to get them to start changing. And this term has another biological equivalence, which we've already seen before, which is, of course, that in nervous systems, neurons are tightly connected to one another. And the values of other neurons, if they're connected to a neuron, they influence that neuron. Okay. So let's try and think a little bit now about combinations here. So let's imagine we have this sum, and let's imagine this weighted sum, again, is a positive number taken as a whole, which means it's trying to increase the rate of change of the ith neuron. And let's assume that t sub I is very close to 0. So meaning this is the Woody Allen neuron. So there's a positive influence on the rate of change coming in from outside. And it's a sensitive neuron, which means its rate of increase is going to be very large. If we keep this sum very positive, but now assume a very large tau sub I, so we have a large value on the denominator on this side, we are still trying to increase the rate of change of y sub I, but it's squashed, or that rate of change, that positive sum is decreased in magnitude by dividing by this very large value. So its rate of increase is going to be much less. So Winnie the Pooh is pushing very hard, pushing Eeyore very hard. There's a lot of force, a lot of positive influence, a lot of excitation coming in from other neurons, but tau sub I is high. So the change in value of y sub I is only going to change a little bit. Eeyore is only going to move a small distance, despite the fact that Eeyore is being pushed very much. On the other hand, if this weighted sum is still positive, but very low, this weighted sum is 0.0001, then there's very little push, very little influence coming from the other neurons. But if tau sub I is close to 0, we have the Woody Allen neuron. We have a neuron that's very sensitive. So with even a small push, this is a positive value very close to 0, but it's being divided by a number that's very close to 0. They may cancel each other out, and you get a value of 1, and the rate of increase is high. So even with a very small excitatory push from the other neurons, this neuron is going to respond or change value quickly. Okay, I realize this takes a little bit of practice, but think about manipulating in your head these different terms. Imagine this is now a very high magnitude negative number, and it's the Woody Allen neuron, or it's the Eeyore neuron. How do these different terms influence one another? Okay, any questions before we push on? Okay, let's add in our activation function, which we've seen before in neural networks several times now. Remember, the activation function is squashing something to a value between some desired range. Unlike before, where we usually take the weighted sum and then squash or push that weighted sum through the activation function, in CTRNNs, the activation function is on the inside of the summation term, which seems kind of odd. The way to think about this is if we look inside a given neuron, that value is not squashed. It can be a very, very large negative number or a very, very large positive number. It's only when we query that number, it's only when we take that number out of the jth neuron and multiply it by the weight of the synapse that connects the jth neuron to the ith neuron. It's only when we extract that number that we squash it. So inside the neuron, it can have any value it wants, but whenever we pull a number out, we're going to squash it. This is the way to think about CTRNNs. Mathematically, it doesn't matter too much whether the activation function is outside the summation term, out here, or inside. Inside. In CTRNNs, it's inside. Okay. Let's add another term, G sub J. So again, let's just talk about notation. You'll notice now that some of the parameters, like tau, have a single index, which means there is a tau associated with each of the 10 neurons. The weight parameters, each weight parameter has two indices associated with it, which means if we have 10 neurons, we have a 10 by 10 set of weights. So for every ith and jth neuron in the neural network, we're assuming there is a synapse connecting them. It's a fully connected neuron. And if we think of that as a 10 by 10 matrix, we can go to the jth row and the ith column, and that value, y sub ji, is the weight of influence between the jth neuron and the ith neuron. So each W is not associated with one of the 10 neurons. It's associated with one of the 100 synapses. Okay. We see that there's a single subscript associated with G, which tells us that there is one G for each neuron. So there are 10 taus, 100 weights, and 10 Gs, and G is meant to represent the gain of neuron J. So let's think about low and high gain. Let's imagine for the and you'll notice the subscript here is J because we're using the gain when the jth neuron, when we're querying it to see how it influences the ith neuron. Excuse me. We're multiplying the value of the jth neuron by the jth gain. If a neuron has a gain of 0 associated with it, its gain is equal to 0, what does that do to that neuron? Imagine we have these 10 neurons. Each of them has their own G, and one of the neurons, the jth one, has a G sub j equal to 0. What can you tell me about Y sub j? So again, we're looking at a continuous time neural network. So we have a bunch of neurons that are all changing in value. They all have their own differential equation associated with them. But the moment we want to know how the jth neuron influences another neuron, like the ith neuron, we multiply its value by 0. As Matt mentions, we've turned the gain of the jth neuron down to 0. The jth neuron has no influence on any other neurons. It can still be influenced by other neurons. If we think about the jth differential equation among our set of 10 differential equations, the jth one can still be influenced by other neurons as long as they have a gain that's non-zero. By tuning some of the gains, we can change the influence of the neurons on all the 10 neurons that it connects to. Okay. We could do the same thing by setting all of the 10 weights emanating out from the jth neuron. We could set all of those to 10, which would also, silence the jth neuron. Why introduce this gain here? Any idea? So by tinkering with or altering the W's, we can alter the influence of one neuron on another. By tinkering with gain, we're tinkering with the influence of individual neurons on all of the neurons it connects to. Any ideas why the creators of CTRNNs might have included this? As Alex mentions, it's an easy way to amplify the influence of a neuron. And again, G is modeled on the behavior of biological nervous systems. Some neurons just happen to have more influence on other neurons. They're supersized, they're muscular, there's something about them that just causes them to influence other neurons more, above and beyond the strength of their connections to other neurons. As we're going to see in a few minutes, or maybe next time, we're going to see some experiments in which CTRNNs are evolved. We've talked about evolving neurons before, where we're going to evolve or change the weights of synapses. So we're going to evolve the influence of one neuron on another. In CTRNNs, we can evolve the taus, the W's, and the G's all together. If evolution, quote unquote, decides that one neuron should not have an influence on the other neurons, or as Alex mentions, there may be one neuron that should have greater influence on all the other 10, evolution would have to find a series of 10 mutations that affect all the 10 outgoing neurons, the outgoing synapses from that neuron, which is maybe unlikely to happen. The probability that all 10 of those mutations will happen and produce that high influence neuron, assuming under some conditions that it's useful for that neuron to have high influence. Instead, one mutation that increases the G of that neuron will, with one mutation, make that neuron have a greater influence on its 10 neighbors. So it's just by introducing the G's, we give evolution another option, another way to influence the behavior of parts of the neural network. Okay, let's keep going. We're going to introduce now theta sub j. So again, we have one subscript. So we know now that there are 10 thetas, one theta for each neuron. You'll notice now it's in the very, it's on the very inner part here of y sub j. So we are adding this value to y sub j. So it's the bias associated with the neuron. What is this bias doing to the neuron? What can you tell me about a neuron that has a positive theta? Or what can you tell me about a neuron that has a negative theta? Remember that inside here we've got y sub j, and we're trying to extract the value, the outgoing value from y sub j, and then we're going to squash it by the activation function. So now once it's passed through the activation function, we have the value of y, multiplying it by its weight, and so on. What does putting in this theta do? How does that influence the value that we read out from the jth neuron? Alex says it determines if it's exciting or inhibiting. Ethan says a neuron with a negative theta is less likely to activate. Not quite. Not quite. Close. I think it's Alex is closer to what's really going on here. Imagine that the value of y sub j at some point in time, this is y sub j here. Imagine at this point in time, the value of y sub j inside here, inside the neuron, the value is 0. If it has a positive theta, then that means that even when the value is 0, the bias means that it's positive. If you erase all the other junk that we have here and just leave minus y sub I, and we assume that associated with y sub I is a positive theta, it means that even if it's 0, when we read it out, it's a positive number. So we're influencing the resting potential. The resting potential of the neuron. It's always positive. It's always excitatory. Its influence when we read it out is a positive number. If theta is a negative number, that means even if the value of y sub j at a given point in time is 0, when we read out that number, we get a negative number. Its default value is negative. If the value of y sub j is very, very positive, and its theta is somewhat negative, then when we read out the value from y sub j, it's still a positive number. But we're basically, by tuning theta, we're tuning the default value of y sub j, right? By making theta negative, most of the time this overall term is going to be negative, which means it's having an inhibitory effect on whatever it connects to. If its theta is positive, then usually when we read out the value, or more often when we read out the value, its value is going to be positive, meaning it's excitatory. It's influencing or trying to raise the value of the neurons to which it attaches. Okay, I realize this is getting a little complicated here. We've got one last term to add, which is definitely an abuse of notation by the authors here. This is uppercase I sub lowercase I. The uppercase I is meant to indicate input to a neuron. I've said that, or assume that we have 10 neurons. They're all connected to one another, but a subset of these neurons. Actually, I'm going to draw this at the top here. Hopefully you can see this. I'm only going to draw 5 instead of 10. But if we have a fully connected neuron, we have something that looks like this, plus all of the self connections. Right, so we have a fully connected 5-neuron neural network here. A subset of these, we're going to set a subset of these to be sensor neurons. These sensor neurons are going to be, as the name implies, receiving values from external sensors. So obviously in this course, all of our neural networks are going to be put inside of a robot, and we're going to wire up a subset of those neurons to the sensors in that robot. And we're going to wire up a subset of the neurons to the motors of the robot. So when we're computing, so in this case here, in the cartoon example here where we have 5 neurons, two of them are sensor neurons. So 2 of the differential equations have this additional term attached, and the other 3 differential equations do not have this additional term attached. As we are integrating, or as these neurons are continuously changing their values, from time to time, a new value arrives from the sensor, which instantaneously changes the rate of change of that sensor neuron. So if this is a touch sensor, imagine that this value can suddenly switch from +1 to -1, or vice versa. If this value is +1, +1, +1, and suddenly that object comes off the ground and the touch sensor inside that object suddenly drops from +1 to -1, what can you tell me about that sensor neuron? What is that? What's the effect on that sensor neuron the moment its touch sensor switches from +1 to -1? And let's say it continues at -1 for a while. How does that influence y sub I, this particular sensor neuron? The right-hand side of the equation, one term on the right-hand side of this equation has suddenly gone from +1 to -1. We don't know what all these other terms are doing. It decreases the rate of change. It doesn't decrease it, it makes it negative, right? The rate of change becomes negative, or it adds this negative term to whatever else is going on over here. If all of this stuff is already negative, then this additional negative value is actually increasing the rate of change. It's increasing the downward plunge of the value of y sub I. So it's not decreasing the rate. If this value approached 0, that would be decreasing the rate. So it's starting, if this value starts to become -1, it's trying to again pull the rate of change to be negative. If this touch sensor is firing -1, -1, -1, -1, and suddenly that object comes into contact with the ground and switches from -1 to +1, now suddenly the rate of change is being made more positive. It's trying to get the slope to increase rather than decrease. Alex, I apologize. Maybe by decrease you meant make more negative. If this whole thing becomes closer to 0, it decreases the rate of this. The rate slows. If this whole thing becomes more negative, it increases the downward rate of y sub I. If this whole thing becomes more positive, it's increasing the positive rate of y sub I. Okay. We've reached the end. That's it. Okay, so we have our continuous time recurrent neural network. It is fully connected. Every neuron is connected to every other neuron. As before, we have a subset of sensor neurons that are receiving information from the outside world. These neurons are influencing one another, but a robot that's equipped with a CTRNN and is being controlled by a CTRNN, the neurons in that neural network are changing continuously over time. That's the main difference between most other neural networks. The other change is that we are going to wrap our optimization process around this CTRNN equipped robot. In our case, this optimization method is going to be an evolutionary algorithm. And unlike other neural networks, we're trying to optimize or find good values for all the W's. In a CTRNN, our evolutionary algorithm is going to look for good values of all the W's, all the taus, all the g's, and all the thetas. So far, I've been talking about a CTRNN with 10 neurons or 5 neurons. What happens if we have a CTRNN with 20 neurons? How many evolvable parameters in total are there? If we have 20 neurons, we have 20 differential equations. How many taus, w's, g's, and thetas can evolution play with? If you have an idea, go ahead and type it into chat. If we have 40 neurons and 40, did I say 40 or 20? Oh gosh, 20. If we have 20 neurons, how many evolvable parameters do we have in total? How many taus do we have? The taus have a single subscript. So we have 20 neurons, we have 20 taus. How many w's? We have two subscripts. We have two subscripts associated with W. We don't have 21. If we have 20 neurons, and every neuron is connected to every other of the 20 neurons, including itself, we have 20 times 20 weights. We have a total of 400. So far we have 20 taus and 400 W's. So we have 420 evolvable parameters so far. How many G's do we have? We have 420 plus how many G's? We have 20 G's, so 420 plus 20 G's is 440. How many thetas do we have? We're converging on the right answer here. We have 20 thetas. So we have 20 taus plus 400 W's, 420, plus 20 G's, 440, plus 20 thetas, 460. The y sub i's, as mentioned here, this might have been a little confusing. There's a couple of guesses of 480 here. The correct answer is 460. We are not evolving the y sub i's. I get that this is a little confusing because we've got these subscripts over here. Remember, we have 20 differential equations that are describing the rates of change of the y's. So any reference to y's on the right-hand side are not things that we are evolving from outside. They're the values of the neurons. Oh, I'm sorry. So Lucas says he was including the L sub i's, or the I sub i's. Again, I'm sorry, this is confusing. This is not something that evolution can play with. These are values of the sensors. So we have the values of the neurons, which are the Y's. We have the values of the sensors, which are the uppercase I sub lowercase i's. The only things that evolution can play with are the parameters, which are taus, w's, g's, and thetas. Okay, we have 1 minute left, so let's just pause here. I think this is a good place to pause for for today. Before everybody leaves, you have a quiz due tonight, but just as a reminder for those of you that came late, this coming Tuesday, I will not be here. There will be one of my PhD students will be a guest lecturer visiting. He or she will be telling you about their PhD research and what it's like to be a PhD student. So for those of you thinking about grad school, bring your questions. This will be a great time to do so. Despite the fact that I won't be here, the assignments will continue on pace. Your assignment 5 is due this coming Monday. I put up assignment 6 for you already for those of you that want to get started. And assignment 6 will be due not this coming Monday, but the Monday after at 11:59. And I will see you a week from today on Thursday. Now that I'm saying that, I will not be here for lecture on Tuesday, and I will not be here for my office hour on Monday, but I am here for my office hour today, and I'll be here for my office hour next week. Amanda, the TA, I believe, will be here as usual. Thanks very much, everyone. Have a good week, and if I don't see you in office hours, I'll see you back here Thursday morning. Have a good rest of your day. Bye-bye.